Yeah. Okay, welcome everyone. We are very happy to have Prithvi from IIT Palakkad. He's going to tell us about heat transport from in solvable models for me.
So thanks BTP for hosting. It's great to be back in TIF for a very long time. So I'm going to talk about some very simple quantum mechanics systems and study of heat transport in the system. So this work was done with collaboration with Narayan from IIT and Sachdev from IIT Palakkad. So it's not this one.
Somebody should be able to fit. Somehow we said to. Oh, yeah. No, but this. Oh,
okay, so this is the overview of my talk. So I set up the question, basically the heat transport and the model that we're the setup that we're working on. Then I'll discuss various toy models for reasons which will become obvious later on. I'll call them RMT and conformal models. Then I'll discuss the third model, which is a little bit more realistic. This is the Sachdev model in one very particular solvable limit, which is called double scaling limit. Okay. So the question I'll ask is what happens when we connect two systems which are held at two different temperatures. So there is one which is hot, there is one which is cold. Hamiltonian would have to start with the Hamiltonian is the sum of the two independent Hamiltonians.
Sorry. I don't know how to. So the system, the system is
recording in progress.
Or is prepared in a state and then
there is no heat bar. The system is just here. There is one hot system, there is one cold system.
So DH just represents the initial state.
Initial. And then I ask the question, what happens if I put them in contact with each other? You could have done it in more ways than what I showed here. The way I will do it is just say, pick some operator from here and an operator from here, add it as an operator coupling, which kicks in only after time t bigger than 0. Okay. So what you expect to happen is some kind of heat flow. The hot system will cool down and the cooler system will heat up. So this is a typical expected plot. Let's say you look at the energy of a hot system. It starts from somewhere and it does some, initially there will be some transients. It will, in fact, gains energy. The interaction has some extra energy which will get pushed into the, and this happens for both hot and the cold. Both will initially increase.
Just because they heated it, right?
Yeah, the interaction has some energy. And then there is a sustained period of heat loss. So heat current is, okay, we'll talk about heat current. This is a heat loss. And eventually it will equilibrate at some new equilibrium temperature. So instead of energy, I look at energy currents, which is a time derivative of energy. That's a little bit more easier to deal with. So as I was telling, initially it will start from 0, and then eventually it will be 0 in the thermal equilibrium, but I'm not plotting it all the way till they're here. In this, I'm just showing some initial transients, some jumps, and then the steady state heat loss that I showed here, there's a linear behavior, will correspond to a constant heat current.
Well, it was the coupling of the two systems instantaneous?
Yes, theta of t. You can have it. I turn it on at t equal to 2.
Also, in that previous graphic, the initial temperature rises.
You can't really talk about temperature because the system is not thermal yet. At very long time, it will be thermal. Initially, it was thermal because you left it at that state. Here, there is no temperature defined, but I can define energies. You can calculate.
And the linear response regime will be towards the very end, right?
Like this regime would be the linear response.
But at least I was thinking close to final equilibrium, because in final equilibrium, if you perturb it a little bit.
Right. That is, yeah. So maybe there is two kinds of linear response, I would say. There is eventual linear response where you look at it from this side. And there is this, which is what is most interesting for this talk. This will be some kind of non-equilibrium steady state. This is what happens if the systems are too big. And then you let them in touch with each other then for a very, very long time, there will be some constant rate of.
I see, I see. It's not like one is a system which you are probing as you do.
No. These equally big size systems.
I see, I see. So
Yeah,
that's
that's
still different, but there's a sort of steady rate of energy.
Steady rate of heat
flow.
loss.
Again, with maybe some kind of heat equation. You'll show.
Heat equation, if there is, yeah,
You'll show whether or not.
So I'm not able to understand why is there a linearity in that.
I mean, it's expected.
Yeah, that's what I'm asking. Why is it expected?
Why is it expected? Yeah, the idea is that if you take very big systems, two big systems, and then put them in touch with each other,
Yes.
it will just be like, taking some, let's say, rod, keeping two ends of the rod at very high, one at high temperature, one at cold temperature, and seeing what happens. What you will see is some kind of heat equation.
Why is it linear? That's what I'm asking. Why is
The Q dot will be proportional to temperature differences. That's what you expect. That's the thermal conductivity. This is the Fourier's law. This is the Fourier law. If you keep two temperatures, two kept ends of a rod at different temperature, then this is a standard thing that you see in many systems. Fourier law. Okay, so this is the heat current, and for what I'm going to do, this will be the main observable. Okay. Now let me set up the system a little bit more technically. So what as I was saying before, there is hot and cold, and then putting them in touch with each other at some time t equal to 0. And what I want to compute is EC dot. Of course, the setup is just to say, you have an initial density matrix rho naught, as I was saying, which was thermal, and you have this HT, which revolves under the full Hamiltonian, and you compute its space. And that would be the heat current. So this, of course, is hard to compute. We can make progress in perturbation theory. For example, if the strength of the coupling is epsilon.
And what you're computing is the expectation value of the Hamiltonian of the unperturbed system.
Yes, right. As against, is there some other?
Now, if you take Hamiltonian of unperturbed system 1 and Hamiltonian of unperturbed system 2, that is no longer a conserved thing, the sum of those two. So that it's not like those two are the sum, the total energy of the whole system. So it's.
Yeah, for example, that if you do the same plot for the cold system, it will also show a bump.
Yeah.
So it's not conserved.
Yeah. So it's sort of not quite the energy anymore because you've cut down the interaction.
Yeah.
This is also different from taking the full system and doing partial test over the hot system first and then computing.
You can do that also. That's one way of thinking about it. You can integrate out the right system. Can ask what will be the effective thing.
So, actually, I have a question which we can clear after Shiraz's thing. Let me ask you, if you wait very long, then would you expect that the full system, hot plus cold, is now described as a density matrix corresponding to some final temperature for a combined Hamiltonian?
Yes.
And that's what you expect, right?
The total H, there will be some beta equilibrium times H. That would be the eventual density matrix or whatever. Yeah, but I will not have much to say about thermalization. So
but approximately or exactly it can't work, right? Because okay.
I was just thinking
exactly it will not work, I think, because it's going to be it will be some kind of ETH true.
Take very long time. Then if you have an efficient enough coupling and you have this full Hamiltonian, wouldn't the full system you expect to be at some temperature for the full Hamiltonian?
I was thinking that the entropy of that final thing will be different from the entropy of the initial.
It will be different. The entropy will become bigger.
And that's consistent with unitary evolution.
I see. You're looking.
I would say weaker statement for all practical purposes. It would be effective temperature. But whether the exact density of matrix will be exactly captured by that time.
Okay, but up to some very fine grade, it should be approximate.
I agree.
Okay, but very fine grade.
Yeah.
Okay. So to make progress, you have to do perturbation theory, let's say, and at the second order in perturbation theory, you will see
How big are your systems big in some way?
Yes, that's what I'm going to do. Eventually, there will be SYK with large n, but yeah. And the heat current depends on the 2-point functions of the system. That's what it depends on. That's the input from the systems that you need. Okay. So the questions that you'll be interested in is, as I was telling, transients, the initial bump, let's say, and the approach to this non-equilibrium steady state, and eventual the non-equilibrium steady state. And I will not be interested in the thermalization. Well, I can't compute it in this particular case. So the more sharper question is this: can we show that there is an energy surge in the beginning, or please see how it goes? When I say there is an approach to this non-equilibrium steady state, how is it? Is it exponential or power law? That kind of question I can ask. And eventually, in this NESS, which is the Fourier law, which is that the heat current is proportional to the temperature difference, you could ask what's the thermal conductivity. So these kind of questions I'll be interested in.
So non-equilibrium, that region means that Th minus Tc is very small. Almost
right.
Close to equilibrium. That is very small, so that's why you want to look
It will
at
be proportional
linear
to
one.
Th minus. In fact, I can do it even Th minus Tc is not very long, small, because at the level of calculations I can do it, but it doesn't. No, there's nothing very physical like thermal conductivity that I can extract.
Where is that equation coming from? The second one, the EC dot is equal to 1.
It's just perturbation. Just perturbation. You do time evolution of, let's say, density matrix or of this operator, and then you'll see that. Second order.
Yeah, so the cold and the hot system, they are finite, so that
Eventually, I'll take infinite. Yeah. So I have not yet told it.
NESS would require that the hot and the cold must be thermodynamically large, so that
Yes.
the heat is issue.
Yes, yes. They are large in my system. They are large.
There is no thermal equilibrium at the end. What so we can
Right. So all of this is approximate. This is like an NESS-like regime. So I'm not saying it's literally NESS. So it will be approximately linear. You can extract some kind of thermal conductivity.
But it's still changing with time.
It is still changing.
It's no stationary state. It's just something slow, quasi-stationary.
Slow quasi. Yeah, you can extract. But in the practical calculations that I'm going to do, it's going to be infinite systems where you can exactly get this linear. So these are the sharp questions I will ask. Okay, and then just one more slide about what do I mean by. So what I want to do next is like I want to kind of set it up for solvable models. I'm going to look for systems where I know the G and see whether I can compute this and to what extent I can compute. So that's the question I'm asking here. With G of T known, can I compute in place where heat current can be explicitly computed? So let me just outline the problem. If you just start with integrable models, of course it doesn't thermalize, but anyway, thermalization is not my aim. But you can't even have an NESS-like regime. So let me just kind of give an extreme regime. Sorry, non-equilibrium steady state. If I say steady state, people don't like it. So that's why I have to say it.
Non-equilibrium steady state means some flow is.
Yeah, something else.
I have a question.
Yes.
So why did you not include the interaction term in the definition of current, the heat current?
Yeah, that is my definition of current. I'm going to look at the code system.
Isn't that going to be an order epsilon contribution to the current while you are calculating something epsilon square?
No, this is just my choice of what I mean by current. When I say current, it's just time derivative of the cold system.
Okay, but is there a particular meaning?
It's not a conserved current if that's what you want to.
No, I mean like why not include half of the interaction part or something to the system's current? For example, if you thought of like coupling two systems by surface contact, like you would expect half of the surface energy to be like shared between the two systems or something, right? So that's like OCOH, and it seems to be an order epsilon term while this is order epsilon square.
Yeah, I can't comment on it, but I did think about in some other place, for example, even the surface interactions can also be modeled. It is just this operator has to be some surface operator in the field
Yeah,
theory.
in that case, you will have to include that to the current. That's all I was wondering.
Yeah,
Thank you.
that might be true, I guess. I don't know, but yeah, I can't comment on it because I haven't thought about it. But this is my definition. That's what I would say.
My suspicion is that is like some knock, but that doesn't build up over time. So initially there's some fuzz, but over late time this will be built up.
Yeah, that's also possible. You mean it will die out, whatever the extra current is.
That doesn't keep going, whereas this keeps going.
Possible, I don't know. Yeah.
I guess if I can comment on that. So I think the coupling term has to be picked in such a way that it has zero expectation value in the initial state, and whatever expectation value is generated, that must be perturbative in epsilon again. So
yeah, sorry, that I forgot to mention. This whole calculation was with an assumption that the O operators themselves have zero expectation value.
So then it will not be order epsilon, it will be order epsilon square at least.
That is true.
But that's probably why you're getting an epsilon square here also. Right? Otherwise,
right. Yeah, you would have some first order here.
You would have.
Yeah, as I was telling, what's the abstraction? Just to say an extreme example is this, that if you take some integrable here, let's say very trivially harmonic oscillator, the 2-point functions will only have oscillations, pure oscillations. And once 2-point functions has two pure oscillations, the energy current, which was the sum integral over 2-point function, will have pure oscillations. So heat current will not show anything. That's fine. You might now kind of reverse this logic and ask what might do the job for us. If you can just go back and see the formula, it's a 2-point function integral. If the 2-point function dies off, then there is a reasonable chance that you will have a finite or some kind of fall off in the heat current. So you might anticipate that you need some kind of finite lifetimes or interactions. And then once you add these interactions, it becomes slightly harder to solve it exactly.
So how does that graph look in the integrable system?
It will just have oscillate.
Yeah,
there is no time scale. Anyway, even this might not solve the problem, but to start with, at least this is something that you need.
Okay, sorry, first asking this, what is the definition of an integrable model? Meaning, suppose I had a system with n degrees of freedom and one conserved charge. Okay, what's the exact definition?
Yeah, I'm not committing to that exact definition.
Okay.
But I'm just saying that you might require something which has some kind of lifetime. Some kind of quasi-particle lifetime.
Things should die out.
Things should die out, otherwise you won't have.
Is this true because of the specific nature of the coupling here? I mean, you could imagine a sufficiently random coupling between two integrable systems that actually shows some features.
No, this only depends on the 2-point function. Unless the 2-point function dies out, it won't.
Right.
This integral won't converge.
But the reason you see this 2-point function is you pick the specific coupling.
I picked any operator, any generic operator from here and a generic operator from here.
Okay.
And I put them in touch with them. So, okay. And what I see is the 2-point function of this generic operator.
You're doing it in perturbation.
I'm doing it in perturbation theory. Right.
So you might take two free fermions on the same two trying start with a state, but that side is some temperature, right? And so free fermion system would be integrated.
Free fermion system would be integrated. Yeah.
Over time, I would see that over a long period, there will be some time where it will the current will flow. And there will be a profile. I didn't understand the oscillation part.
You need something also. Just free fermions won't do the job, right?
It's an integrable system.
So there is no time scale associated. So what would be the time at which the NESS regime would?
It will not reach NESS.
Yeah, it will not reach any. Yeah. So there is no steady heat current.
You're talking about the steady
state heat current.
I didn't get the oscillation.
No, I'm just okay. Maybe this one is a little bit very sharp in the sense of, okay, not very sharp in the sense, very specific. I'm not saying this is just one example. I'm not ruling out things. I'm just saying this gives you kind of an idea about what kind of physics you need. And the physics I wanted to kind of say is that interactions is there. It's kind of intuitive. You need interactions, otherwise things won't start going into the other.
But just to follow up, suppose you have two big free systems. Then there is just free field theories, as Prithvi said. Then there's no KT, both were massless free field. So you have there's no particular associated frequency. All frequencies are there because you have all Ks.
Okay.
Okay. So then you could get quite complicated behavior, which probably won't be your NESS anyway. But it will be less trivial than this as well.
Yeah, it will be less trivial. Yeah.
I mean, as Gotham has hammered home over 10 years, there's a sense in which free field theories look like the thermal-like. You start with some state in a free field theory and you wait long enough, a little bit of it can become very close to the, if it's started in the right state, it can become very, very close to a little bit of a density matrix. Carnegie also has. Yeah, so and then what was important was that it was very big. If it was a free field theory in a box, it would keep coming back.
So big was okay with me because big is what I also have.
But I mean, it's big, not just in Hilbert space, but in space.
Maybe.
Yeah, that the K, that omega.
Yes. Yes.
That there's no
sufficiently.
Yeah, that there's a dense spectrum of omegas.
That is. Well, I will say something in the next slide, but I might as well say it. So what I'm going to do is just quantum mechanics and not even have one dimension. So in that sense, for these systems it will be not true. But I guess in 1D I could.
But even for quantum mechanics, if you've got like n oscillators,
right,
you could have a continuum of frequencies.
That is true.
And then it's less clear that
this will work. You're right. You could. I guess what you're saying is this: you could have a spectrum.
Yeah.
Where you choose the spectrum such that it's sufficiently complicated and it has, there's some.
One example is an example of the discrete spectrum.
Right.
Discrete spectrum of frequencies, that is sort of very clear as oscillations. But if it's a continuous, almost continuous spectrum.
Right. I agree.
That will be similarly a random matrix.
Yeah.
If you had a self-averaging version of random matrix theory, it would be a single system, but with a.
Yeah, that will be one of the.
And then it will be what Shiraz said.
Yeah, I agree.
And that's like a sort of single instantiation.
Yeah. Yeah, maybe we'll come to that. Yeah. So just to kind of see what do I mean by G's, the two-point function is actually, if you know the spectrum and matrix element of operators, then that's equivalent to knowing the two-point function up to integral. So when I say known G, I'm also willing to say that if I know density spectrum and the average matrix elements, I know G. It's like still solvable.
Sorry, in answer to I think Amit's question, you said that E dot was this because of perturbation. You have one line explaining why.
No, I don't have it. But I can. This one you mean?
Yeah.
This is
GC of what?
The GC is the two-point function of the cold operator.
Cold operator?
And GH is the two-point function of the hot operator.
I see. And this is because these were the operators added to the Hamiltonian. That's why some of it affects E.
At least in zeroth order, you don't have a non-trivial one-point function. That is two leading order. So you need two inserts.
You just put two evolution operator, integral dt, hi of t. You will get some this kind of.
I see. Thank you.
And there's more to it.
Yeah.
It just looks like Fermi-Golden.
Yeah, I think Fermi and Golden's rule will be consequence of this formula. Yeah.
I see. So Fermi-Golden rule meaning you already need some energy I state, and then you scatter it to some others. That is.
Yeah.
Yeah. So this formula might look better than that. Yeah.
Thanks.
So what I mean by solvable models is where I know the spectrum and the average matrix elements. Okay, so and this is the disclaimer. I'm going to restrict to quantum mechanical systems, so there is no dispersion. And the models that I study is I'll study three kinds of models. Two toy models: is random matrix theory and conformal models. What they are, I'll tell you. And third is a little bit more realistic, which is the Sachdev model in a very particular limit. Okay. So first I'll talk about this RMT-like model. So if you remember what I told you in the previous slide, the solvable models means I know the spectrum and I know the matrix element square, averaged matrix element square. And this can be extracted by the property of matrices, let's say the Hamiltonian of the operators. So this kind of question, random matrix theory is perfectly suited to address. So for example, you could ask what is rho of E in a typical random matrix theory model. So if you take unitary random matrices, you get a Wigner semicircle. Okay, so there is very little parameters here, just the cut distance is all there is. That's not enough. I need to have a averaged matrix element square. I need to kind of give what is the value of this. While random matrix theory itself doesn't say anything about it, I will just make an ansatz and I'll kind of try to sell that ansatz to you, and I'll just take the, what's the simplest thing you could do is put a constant, and the next simplest thing you could do is put some kind of simple even dependencies. And this is what I will take to be the model of the matrix element. Now, why is this reasonable? At least low temperatures, I would think it's quite reasonable, because at low temperatures, by the way, the energy is only supported on a cut. In this case, it's only between -2 to 2. So at low temperature, everything will be only depending on the ground state properties or the vicinity of ground state. So all this E1, E2 will all be very close to being the ground state. And the average square would be some constant. So that would be the kind of justification for F0. And delta is the simplest thing that I could do in power series Y.
We could also this be given by this what we call that.
ETH, right. Yeah. So that was the next thing I wanted to say. If you take ETH answers, ETH also has this kind of answers. If you remember, the matrix elements of any operator has some diagonal component, which is big. It depends on the thermal value. And then there is another correction, which is typically called F in a random matrix theory literature, which is suppressed by entropy, e power minus s. So F is not given, ETH just works for any F. So this would be the choice of F. This would translate to saying that.
So this is not for the diagonal elements. This is
F0 will be there in the diagonal elements also.
so the other term.
The other term will be a choice of.
But then wouldn't it be suppressed hugely? That's what.
Yes, but this is average square. So there will be some more states also in between.
Okay,
right.
That gets rid of
that. Gets rid of that. Anyway, so this is the model.
So rho of E is just the density of states of the unperturbed Hamiltonian.
Unperturbed Hamiltonian.
And now you're going to put this at finite temperature. You're going to study this.
Yeah, that's all. So just the parameters of the model is E0. What in this case it's 2, but
and the comments about low temperature, when we made them, were saying that your density, the matrix elements may have a different structure, but your density matrix will the states that you're looking at will only have support
only in a very vicinity.
So you don't care if it changed. Yeah.
Right. So the main thing is that the parameters, there are very few parameters in the game. So there is only the cut distance and this delta. And you could ask what is the, what is the consequences of having such a model on Kitaev.
So I didn't understand how this entropic suppression goes out.
Right. So I think there is two kinds of things. One is, I got the details, but there is, when you do the average square, you have to sum over all intermediate energies. I mean, intermediate states at that energy. So the ETH suppression was e power minus s of some kind of E bar, which is the average energy times f of E1, E2, something like this it was. And then you need to sum over all. So this is what, you want to n, let's say. And, yeah, this might be a little bit more detailed than I'm not even sure. So for example, if you do the sum over n, there will be many states with the same energy. And they will be roughly scaling like S of E bar, E power S of E bar.
But why are we summing over? And I mean, this is just a point-wise average, right? I mean, you have this matrix, E1, E2 matrix, and you are squaring each entry. and then averaging.
Then average, yes.
And not squaring the whole matrix, which I would imagine would have this intermediate state sum.
Now, what appears is the full, yeah. So here, what it appears is if there are more states, you would have to sum over, like there will be some, kind of this degeneracy labels to it, and you would have to sum over all states with that. This row of
this is the level at which the sum will appear.
Yeah.
But that formula was.
Yeah. So if I use this, then I cannot use row because row will take away that. Row will also have some exponential.
So
SOP bar.
So what you're writing is a row times that.
Row times that.
That helps me.
Okay.
I also don't understand why.
Yeah. So
Okay.
yeah, I didn't direct. Yeah, here I didn't put that, but
Then it makes sense. Then I understand. Because actually, I think what eigenstate hypothesis is minus S by 2.
Yeah. That's why
right.
It becomes
Sorry.
S. And then that S, which I also. Thank you.
But then can you write what appears on the right hand side, next slide, explicitly?
What appears on the right hand side meaning?
Yeah, so here you are saying what you're writing is not quite the left hand side, but left hand side.
No, left hand side is fine. Everything is fine in continuum notation. The trouble occurred when I tried to connect it to the ETH ansatz, where I typically use the discrete notation. So, for example, here when I do the sum, it would actually be a integral over dE, the rho e here. That's what I would write in continuum. So, right. I mean, if you don't take the ETH, then what I say is okay. But if you want to make the connection to ETH, then you will have to change intermediate format.
So in your integral, would you replace rho times this with f?
No. This is just the matrix elements. This is what enters the. That's what I guess.
You replace the yellow stuff with f.
Yeah, the orange stuff I'll replace with F naught.
But then there is an extra row there, right? Which you just said that you used to remove that entropy.
Yes. So in continuum notation, it's fine. Right? I mean, this is an ansatz. And I'll take that F naught to be the ansatz. Well, let's say delta is F naught is a constant. That's it.
I think there might be one more factor, one by e to the minus s coming from the Gaussian integral of the random approach. Is that it? Because there are also random coefficients, right? This in the microscopic model, E1 or E2 is e to the minus s by 2 times some random.
Yes.
So then you're doing the integral.
Yes.
And that gives you one more factor.
Yeah. So there is some RMN here. That's what.
Yeah. Right.
Yeah. Random matrix. Random matrix in this no, maybe I'm not sure about this because I don't remember, but random matrix in this, I think there is width 1, that's all. It did not have any parameter. No energy.
That is the one that
gets pulled out by this SC.
That is the one.
That is fine.
So in this format, just that rho e is like exponential of entropy, E1.
Yes.
Rho e2 is exponential of entropy. And in that orange thing, is that small or is it order 1?
In this thing, it's order 1.
Then I don't understand. I thought every matrix element was small.
Yeah. Maybe,
now you're saying there are many states.
Yeah. So the way the way it works is that rho e is order 1 for me now. I didn't put any exponential.
Rho e is order 1
for me. That's my scale. I've thrown out all the exponential in entropy.
Then you put it already.
Yeah. This whole business is just because I wanted to connect to ETH. That's all. So don't. This is the usual random matrix normalization where there is no Hilbert space dimension sitting outside. Integral rho is 1. Integral rho dE1 is 1.
I see.
Sorry for the confusion.
I see. And now the S by 2 is worrying me because then it feels like you pulled out 2 factors of S from rho e. But this is only one factor here.
That's why I think maybe the integral over R's can be one more factor.
Everything in this should be order 1. There should be no exponentials in entropy because that has been taken out in some sense.
Which is show your previous slide.
Yeah. This is just insertion of icons.
If I were to write it in discrete notation, maybe a final sum is okay. That is to say, we have sum over E1, sum over E2, and then just some average matrix element, right? And
this is exact. You mean from here to here?
Yeah. The first one is exact.
The first one is exact. Going from here to here, I've not kept track of the fact that row is there.
And one way to do it is you keep the ends in row. You keep row so that integral rho GD is actually the number of eigenvalues.
Okay.
Of the matrix.
Yeah.
So there's an end.
Then there's an end there.
And then I think it should be e to the minus s over 2.
Yes.
Times a random variable, if I remember, with unit variable.
Unit variable.
Yes, and that should be okay.
And then you're getting a total n.
You're getting total.
And is that what you want?
It's
like one n in the row, one n in the row, the other row, and then you're getting 1 by square root n in each of those matrix elements. So you're getting you're getting an overall n, and maybe that's what we want.
Maybe that's what you want.
There's usually a one by normalization.
There is a normalization also.
Okay, so then what you want is that
minus
because it's a trace, there's an end, then you're removing that. Something. Okay, got it.
Usually the two-point function is normalized by the.
Oh.
There's a divide by trace equal minus beta h. That is also scaling with n.
So I think the way to say it is that since it's a trace, you should expect everything to be n. Take that out.
Okay.
That's what's
Normalized with
So I confused you because you talked about the discrete system.
Do not here for every factor of 2 is past master. We'll see.
Wait for the next factor of pi. Okay, sorry. So what I wanted to say was that this is such a simple system. You might think, why will it do anything? But it turns out that it's simple.
Factor 1 billion.
So it does the job in the sense that you see some transient and you see an approach to the NESS regime, and this constant is the NESS. Constant will, the height, eventual saturation height will be proportional to the conductivity.
So am I understanding right that you chose your temperature to be small compared to your gap of the semicircle compared to 2?
No, I mean, this is fairly easy calculation. You can do it for any temperature.
One of your justifications for that was that.
No, I'm going to say this is my model now.
Okay.
Well, let's see what happens.
Okay. So.
You could in principle ask that why is this justified? That's a different story.
This E1, E2 sounds weird. Yes. It sounds like a Taylor series.
Right. It actually, you can write it as a Taylor series in E1 minus 2 and the distance from the 2.
The distance from the 2. So if you're doing something, you've got something like where your state is very highly peaked, it sounds reasonable. Otherwise, it sounds like a weird.
Right. So you can write it as something which is to the quadratic order in E1 minus E0. But in just this, it doesn't look very nice. But this is what I'm taking. This is the model. And the point is that this model suffices even at finite beta to give you something which is reasonable. Okay, so anyway, this model is so simple, you can kind of almost calculate.
Y-axis was heat current.
Heat current, current normalized in some units, epsilon square has been pulled out, like that. And
just to understand, when it goes out, that's your NESS.
This is my NESS state, right?
And it should plateau and then slowly decay.
Eventually, if you follow
different stages.
If you eventually follow it, it should decay, but we are not doing that because we're doing perturbation theory. The formula itself has no validity beyond.
Yeah, the perturbation theory is perturbation important.
In the strength of the coupling?
But was it also in time?
No.
So then why can't we follow it in time?
Yeah, you can follow it to late time. This will be just a constant. Because G of t has died out now. That was the whole, maybe I didn't show the 2-point function. Yeah, sorry. The way it connects to the 2-point function argument that I told you before was that 2-point function, if you compute using this f and e, 2-point function will have a fall.
So what I'm trying to understand is a very stupid question. If you're saying that this works if epsilon is small but at all times, then it seems to be giving the wrong answer. Because eventually we expect the heat current to die.
No, that is if you start doing non-perturbation.
This is what I'm asking. What is your perturbation theory?
The system is so big.
So is your perturbation theory in epsilon, or is it perturbation theory in epsilon times some function of time?
Well, Yeah, so there are two things. If I take my perturbation theory in epsilon very seriously, then I cannot let T to be very large.
Good. So your perturbation parameter is epsilon times some function of time. That's what you're saying.
Maybe there's a way of saying it in terms of that. That's true.
I think that's what you're saying. Now, what function? What is the next correction going to be weighted with compared to this?
Like, is it linear?
Time.
Yeah, something 1 by epsilon, I would think would be validity. I mean, this is a question of validity of this.
No, but the question is, what is the time behavior? Is it T or T squared or E to the T, or presumably we know physically that it's T, because that governs the change of the temperature, the change of the temperature difference. The thing you're not seeing is that the temperature difference has changed.
Yes.
So, and that's like a linear effect. So I think what you're saying is that it's T times epsilon square is your true perturbative parameter. And if that becomes large, the next correction cannot be ignored. Is that what you're saying? And can you, it would be probably 2 lines to justify.
Yeah, we could probably estimate the next order perturbation.
Yeah.
And then say what's the radius of this current. Not trust how far you can.
When does it become as big as what you get?
Yeah, we have not done that, but in principle.
I mean, it sounds important because you're interested in time dependence.
Right, but our argument is not going to be that we will follow up presumably this T will be something inverse in epsilon. It cannot be epsilon independent.
Yeah.
So if epsilon is small, then it's fine.
For your initial point.
For this calculation, it's fine. But I guess that I could say more in the sense that I could trust it even to epsilon to the power something.
Maybe I guess to ask, just say what Shiraz is saying, you in your first curve had the NESS, but then it leveled off, right? And Shiraz's point is that leveling off would be some breakdown of the perturbation theory to get the NESS.
Right.
So if you could estimate that by keeping the next order, you get an estimate of where the NESS ends. Right?
That I think is correct.
And you might be able to do more, because you see, for a long time, you're still getting this Newton law kind of this. Heat current is temperature 1 minus temperature 2. It's just that the temperature difference itself very slowly changes. So this is the kind of thing that a small resummation of perturbation theory can give you.
Yeah.
So that you're tracking not the initial temperature difference, but the temperature difference at that time. This is the kind of thing that very small resummations often allow you to do. So the place will really break down is when the two systems are coming to near the same temperature. Then you will probably require something really much.
Yeah, one problem with this is that at higher orders in epsilon, higher point functions become important. I have to provide more and more data to this story.
But sometimes one set of graphs is important. Like you take a propagator, you have a self-energy bubble. You just put it in the denominator. That's an infinite set of graphs.
Right.
That generates a lot of information.
You can resum that part at least.
Or even just area back perturbation.
Yeah.
Like at any instant, if the specific heat is large, temperature fluctuations would be small physically. So at any instant, if you can approximate the two systems as having a local temperature in time, then you use it there.
Yeah, exactly. There are two separate time scales. There's time scale associated with how much time flow 1 unit of heat is transported. And there's a time scale associated with how much time it needs to change the temperature by an order 1 fraction. And because the system is big, that is a much bigger time scale. So what you're doing is working small times compared to that second time scale. But as Sandeep says, you could do better, I think, by just at any given time working for a small interval, but using the temperature difference at that time.
That's what the large specific heat
Yeah.
I see.
So what heating was not to be just interpreted that way, that it's just that any temperature is moving.
Because he just gets a flat curve.
So what Shiraz is saying that it should turn around sometime.
It should not even turn. It's just first that level should keep going down.
Yeah.
Because it should be proportional to the difference in temperatures.
You're not maintaining the temperatures fixed.
No. I'm just saying this is a large system. It should.
It will take very long since the systems are.
Yes.
But it's like trying to put a hot nail in a bucket of water. So ultimately, it will stabilize.
Yeah, but again, that's just maybe I mentioned it, but he's not here. The real point is that I cannot completely control this calculation because if higher point functions are just decided by the 2-point functions, then it's okay. I don't need extra data. That's this approximation. Sometimes people call it secular expansion or something.
But this time scale should depend on the size of the system.
This time scale should depend
Exactly.
on the size of the system or on the epsilon. Some epsilon also.
Not, yeah, epsilon, even if epsilon is perfect, large, still the time to equilibrate depends on the size of the system.
If epsilon is very large, then maybe it will equilibrate faster.
Yes, faster than smaller epsilon.
So there should be some combination of epsilon and the system size which controls.
Epsilon is 0, no.
Epsilon equal to 0, there is no equilibrium.
But is there a way to interpret this in the way Vikram said, is that you constantly keep the temperatures to be TH and TC, TC? You update the CV, yeah, and then see that would be like providing us non-equilibrium steady state by force.
That would be a true steady state because your heat current will never die out.
And then
right.
And then can I interpret what you got as that answer? Because then there will be a steady current.
Absolutely.
Yeah, that would be true. Yeah, I think that's.
The way I'm thinking is like this: random matrix theory is a very efficient mixer.
Yeah.
So you have some decoupling. Maybe I'm wrong. You have 2 random matrix theories, right? You have decoupling. You inject some energy from one side to the other. It mixes in that side very efficiently, right?
Okay.
So therefore, at every instant, you can use an adiabatic approximation. Like you inject some energy, it changes the temperature on both sides. Now you use the new temperature and fix whatever Fourier law for the new temperature, and so on and so forth. So that's how adiabatic perturbation theory runs, right? There are 2 time scales. Then it should be.
There are 2 time scales. Beyond this larger time scale, it has to perforce.
You're saying this is the time scale, right? Roughly. This is the time scale for the change in temperature. After that, there will be one more such. Like roughly, this is the place where steady heat current starts.
This is where steady heat current starts.
And you're saying this provides a time scale with which you can.
And then if you have some equation like T dot equals CV, so yeah, rather, okay, what is it? Q dot equals CV times T dot, right? Then from there, you make an estimate of the time scale.
Yeah. I think it will be the.
And that CV will sit there, or something.
Yeah, and the bigger your system size is, the longer it will take to reach that temperature.
Yeah, the system size is 1 in this sense because everything has been scaled out. Right.
But if the system sizes were infinity to begin with, then it will forever remain like that.
Remain like what?
Like it will not be able to equilibrate to a common temperature.
It'll just keep.
Because
So it's system size temperatures.
Yeah. Influence system heat.
Maybe coming back to Abhijit's question, right? You could ask what happens if you maintain the temperature. That's what you are asking, right? Yeah. So that I think would need another kind of. I have to couple my system to the heat bath itself. I mean that's another story. Otherwise, how will you maintain the hot systems?
So this cannot be interpreted like that you are keeping the temperatures artificially equal, and then you are seeing that.
No, this order I think can be.
Yeah.
This order it can be that, but there is another question about what happens at next order. Presumably that will show something else. And that I'm not sure.
It's expected that the heat current would just be steady.
At next order? No, that is not what is expected. That is what I think.
No, there is when you maintain the temperature.
When you maintain.
Yeah, that would be a true non-equilibrium steady state. This one has to die at some point.
This one has to
because
die. Yeah, if you work in next order in perturbation theory, it will die. That's right. Yeah.
There's a common temperature, there's no heat.
Right. That's right. Yeah, maybe at next order it will work very constant. But again, the problem is, if you want to couple another bath, then it's not going to be very solvable. That might be my
What are you calculating here from random matrix side?
I'm computing the 2-point function and then the heat current. Using that, the heat current.
So what is the delta related to the original? Delta is this parameter.
Yeah, delta is a parameter.
How is it related to the original?
There was no original system. Here, delta, you could ask what's the physical interpretation of delta. Loosely, one could say it's a cost of how matrix element is, it's something between E1 and E2. And delta kind of suppresses transitions between far off even. That was our loose interpretation. So, yeah. Okay.
So it's not.
No. One extreme example you could say is that if you take the two edges of the cut, it will be 1 minus delta. If you take the two on the same side of the cut, it will be 1 plus delta. So 1 minus delta to 1 plus delta is the kind of suppression that we'll see if you want to see how the states here and here are connected versus how the states here and here are connected. Yeah, it's a loose statement here.
Can I ask a question?
Sure.
So here, should I think of the decrease in energy current as the temperature difference, some kind of approximate effective temperature difference decreasing? Should I think of it that way?
Decrease in energy current in what sense? When you change the temperature?
After time 1, there is a decrease in energy current.
Right. So what's the question?
Should I think of that as arising from reduced energy difference or a reduced effective temperature difference between the two sides?
Yeah, I don't think so.
Normally, when you get a steady current in a Fourier law, you usually keep the end points, the two ends at fixed temperature, and then you get a steady heat current. Here you're getting a heat current that is steady, even though the energy there is a steady rate of decrease of energy or temperature on the two sides.
You're talking about this. I don't know whether you can see my mouse pointer.
Yeah.
You're talking about this decrease, right?
That decrease,
this decrease should not be thought of. It's not yet thermalized or anything. I mean, anyway, it doesn't thermalize in any of this in any part of this graph. But this decrease is just, I would say, it's just part of transients.
I see. And in the later time when there is a steady current, should I think of it as similar to Fourier law? Because it here.
Yeah, it is a Fourier law. Yes.
But there is a steady rate of change of energy on the two sides, whereas the standard Fourier law would have steady temperature on the two sides, which means that energy density on the two sides.
Standard Fourier's law is the statement that heat current is proportional to temperature difference.
Yeah, here on the
heat current is a constant here, and temperature difference was anyway some constant.
But that is only in the initial state. You have here there is no extra energy pumped into the two sides or pumped out of the other side.
Very big system, and he's looking at small times. So you cannot see the change in temperature.
In the random matrix description, I couldn't see a notion of size of the two sides.
Yeah, it's normalized to 1, so that's why you don't see it.
I see. So I should think of this as two large reservoirs connected by a small coupling.
Yeah, I mean, if you want to think of it physically. Right now, I'm just giving you this model.
Yeah.
I'm asking what's the heat current, and this is the answer.
Okay, all right, thanks.
The time scale for the n is independent of n. Is that right?
Yes, there is no n here.
Yeah, the independent of size of the element.
Yeah, actually, that's the reason why I was asking. Is there so it looks like the peak of the energy current happens at time scale 1, and
right.
And that seems to be true for both temperature differences. Is there a mechanism?
No, that I think it's normalized. I don't know. Yeah, this was just to plot it. I normalized it to the same peak height.
Okay.
I think in the next plot I have a peak.
Whatever
peak height thing.
Yeah. Okay.
So let me just go ahead.
This energy deposited because of the transient turning on should be order. That is, to the extent the energy goes up, because you at theta of t you turn on, right?
Yeah,
that's an order.
That is an order 1 quantity.
Now the heat current will respond once.
Yeah, it's because every part is I mean, the same independence in the in the interaction Hamiltonian as there was in the unperturbed Hamiltonian.
Yes, yes.
Just n is
There is no extra n scaling, relative n scaling.
Yeah.
That's Rajdeep, you're asking something, sorry.
No.
Okay, so again, let me quickly ask the questions that we're interested in. What are the transients? What's the approach to NESS? What's the thermal conductivity? So the transients, we see very little dependence. So for example, if I ask where is the peak height, the time where the energy current peaks, it has very mild dependence on delta and temperature differences. Okay, temperature differences are in plot here. So yeah, it had mild dependence on the average temperature. This beta is the average temperature of this peak. And delta, there's no strong dependence. We could also work out the peak height at low temperatures. It was some constant. As you increase temperatures, it decreased. So the peak height, unfortunately, I normalized it in the previous graph, but if you work it out, the peak height decreases. Sorry, I have to share that.
Normally, I would think that very short times you can do some Pavlov rule like calculation of where the energies are going, right? And that will be
this is
a linear increase. You can calculate the next order term, that's where it will turn back. Right? It doesn't have too much to do with beta, it's just initial conditions that will determine this. It's just Pavlov rule, and you're saying, when is the next nonlinear term going to bend it back? And then, of course, the final approach is related to things that there'll be questions about whether that perturbation theory holds that long time, and so on. If you would want to. So then the linear increase is just the Pavlov rule. That's why it's not so dependent on what you are doing.
Do you have a discrete spectrum in your actual calculation?
No, this is just random matrix here. I'm just inputting this, but yeah. There is no discrete spectrum. Even in the DSSYK models, I'll eventually look at this.
So what determines the characteristics in position, right? In time.
I would, yeah. Not the cut distance. The cut distance, I would say. Yeah. I'm not very sure, but eventually, I think this cut distance, random matrix theory has this cut, right? That controls mostly everything.
So the bandwidth, roughly speaking, the bandwidth.
Bandwidth.
Bandwidth is set at 2 or something like that.
Yeah.
So that's the energy scale. That's the energy scale. Inverse of that will be what.
What we see is that there is no strong dependence on delta, and the only other F naught is a moral number that the matter. The only other scale in the problem is bandwidth. That's 30%. That's the makes sense. Surprisingly, this kind of question was not asked. This is two RMT systems. You couple them. I don't know why. It was, I think, it was not asked. We asked a few people, Abhishek, and I said, here. We asked whoever we could ask. We asked, but there was
maybe one comment on this is that not RMT, but a real bunch of oscillators coupled to a bar was something that we did, and where not within perturbation phase, there you can solve the problem exactly. And then you again see this, that there's a linear rise, not surprising. There's a Pavlov rule that short times will not be surprised. But we were, and we could estimate what the peak height and where the peak will be. And then you can see where, so the path starts affecting you only at a long time. The short time is just your Hamiltonian, internal Hamiltonian giving you the scale. So we actually have a paper where we were doing it for entanglement entropy in that case, not currents, but you can show that these things basically do this. You can, by the way, get rid of the peak if you really kept it at high temperature difference. Then what it will do is go up and just go there because its steady state value is so large, it really doesn't need to come. That also happens. You can change the parameters of the bar.
That kind of thing happened here also. Maybe not in this system, where the temperature difference is so big, then it doesn't need to come down. It just kind of keeps saturated. Maybe I'm not aware of all the literature. And then there is some literature where, if you have a bunch of harmonic oscillators, it might itself be well modeled by an RMT. So the thing I'm saying here might be there secretly in the literature.
No,
Because-
what I'm saying is this will be a very general feature. RMT details of the bar changes things a little bit, but this is basically saying there's the short time convertible and then there is a long time steady state which is governed by your bar.
Right.
Where you will come alive or whatever steady time you will.
Bath meaning the system or?
In this case, your bath will, in this case, your final answer will go to 0. Right? Because your
No, not some height.
No, that's because of your perturbation here. If you calculate at higher and higher order, you could go to 0.
Right.
Because it will come.
Yeah, there is one question here which maybe you should also comment on it. So so peak height, peak length. I think this, as you are saying, is fairly independent of what model you use for the system. Thermal conductivity also can be computed. Let me just flash it. It's some.
Can I just ask? I'm really sorry, but you must go on. But just so many experts. I mean, what is the status of Fourier's law? I understand linear response, but as you emphasize, this is not quite linear response, right? You have two big systems, this NESS, right? Is there some statistical mechanics, a kind of proof of Fourier's law? It seems such a reasonable, that dq should be CV times dt. But dq over dt should be, it should be linear in t. Is there a proof of that or not?
I looked for it. I don't know. Ultimately, I think the calculation is this.
Okay.
It, in principle, should have been some kind of what are the properties of G such that.
Okay, it should.
And there must be some kind of analytical properties or something.
With that,
But I don't know whether
about the steady state, right?
And Sandeep,
It's a steady
he is not estimating the evolution of the temperature difference. Because if he did that, then he might well confirm Fourier's. Because the rate at which energy is lost from the hot region to the cold region might well depend on just linearly on the temperature difference, provided the temperature difference is not large.
But he's not confirming that.
But it's not many different temperatures.
Different.
Yes, for this model.
That will
Fourier law is about the steady state.
The Fourier law is linear response, and if you have very big temperature differences, nobody expects Fourier law.
No. But keep this, the temperature difference is small, but you can vary them with your initial conditions. So he will be able to confirm that the current is.
in this model, I'll be able to.
Yeah.
He should be able to.
But you will always get it at the long time limit.
NESS. It's NESS.
Yes.
No, but this is NESS. It's a question of whether are you building up the current or are you looking at the steady current?
No, steady after the trans.
After the transition. Steady current, you should get the answer for your.
Okay, you must know, but I only say this because I thought linear responses, you have equilibrium and you kick it a bit.
Yeah.
And here I thought,
No.
your NESS was different, like you have two
This
large
is different from
regions,
the response.
and it's not a small perturbation. That's why I was asking.
But why not? If delta T is small, why not?
I think it's dependent on the temperature difference, and he's not tracking.
You say just a small temperature difference, then you should.
So linear response always here is what
I see. I'll try to understand.
So Sandeep, I just want to say that in the Fourier law, when people talk about is for an extended system. The system is big enough.
Yeah.
So the difference between the two temperatures, you can think about as like delta T by L. So that is small. So in that limit, you can write it's for extended because you are writing this del kilo as del x.
Then perhaps for each little segment, you use the nearest
You
form.
think of some small, like constraint scale, there you would write that.
Okay.
In this model, I can show that's true, but for me, it would be a model by model statement. I couldn't find a more general statement. Thermal conductivity we could do. There is this one more comment that I wanted to make. This approach to NESS, how the this is not NESS, but anyway, how the NESS regime is approached. What we saw was that there is a power law approach to the NESS regime. So this power law can be easily traced back to the Wigner semicircle cut. So near the cut, the density of states has this square root behavior. And you can kind of trace this t to the power 5 to the square root behavior. This is the singularities control the long time behavior of thing. So yeah, so there's at least here, I would say this is a place definitely where the system details matter.
If that is the philosophy of power law, it's easy to figure out, given a particular kind of non-analyticity, what should be the power. And that matches.
Yeah, that we can actually do. So that's what I'm going to do next. You might ask, is there some kind of universality at low temperatures? This is exactly what I was saying, that we could kind of trace that some of these things have everything to do with only the ground state behavior and what's the nature of the singularity of the density.
So were you to smooth that out, you will get an exponential.
Yes, that also we have later on some other kind of smoothing out. We'll see what happens. But at least here, what we said was that, density of states, what happens if there is a power law singularity? Instead of half, we could say some alpha. We could just, anyway, inventing models, I might as well invent a model. We couldn't find a microscopic version of it where, random matrix theory gives you root. But if there's some other matrix model which gives this, we could not see. In fact, mostly I think there is a general statement that it has to be a square root kind of singularity in matrix models. But anyway, we just write this model down and we could ask what happens. And this is just as we were saying, you could, for example, the conductivity goes like a power law, which depends on alpha. Approach to NESS also goes like power law. For alpha equal to half, it of course matches the random matrix theory. But we could write down things.
Shouldn't the NESS ultimately the time scale should somehow depend on your non-equilibrium temperature, whatever is the final temperature. There is a time scale imposed by that. Should be somehow.
Equilibration is not happening. Sorry, maybe I didn't.
Meaning like you should be exponentially close to NESS beyond a time scale 1 over T star, which is your equilibrium temperature. Which is once the two have come alive, we at midpoint something. So that beyond that time scale, you should have a true steady state. Whether that current is 0 or finite, whatever it is, but it should be the steady state. Because this is like I can see that if it's a 0 temperature, it can forever go up and it never.
This is true. This was basically our paper with Anand that if your vast density of states has any singularity, any non-analyticity, you always get a power law approach to equilibrium.
So it's truly just due to the singularity.
Now, in your real system, there will be also scattering from whatever. But if you have a singular density, in the real system, all singularities are kind of smoothed out on time scale. But if you really had a singular answer, and you would realize this because it's simply the statement that you give me a singular function, its Fourier transform has ringing mode with powers. It's just coming.
Right, there's some scaling.
It's just coming from.
But in a realistic situation, it should depend on the temperature. Like beyond that long time scale, there should be no difference. It should be exponentially close to the NESS.
No, but that's the point. There's no exponential. Your long time behavior, you reach really at infinity, but other
minus T star T. Like if there is no singularity.
If there is no singularity, then yes.
Then
it has a singularity.
Yeah, so it's coming from somewhere.
Maybe I'll just go ahead. Sorry, I think I'm not going with science. So how are you with time? It's in the grand tradition of TIFR.
At least.
How much time do I have? Abhijit, what do you think?
In 40 minutes.
I think it's fine.
So the sensitivity will be fine.
So let me just move on. So now I'll just look at a different kind of model. So here what I will do is, this is motivated by the conformal quantum mechanics. So you could ask, what happens if there is a power law in tempering?
Sorry. So different kinds of matrix model are corresponding to different types of Hamiltonian or totally different systems?
They will model different kind of Hamiltonian. Yeah. So here matrix model will come as a parameter.
So for different systems, which Hamiltonian?
That is I don't have a Hamiltonian. That is the only input I need to compute the heat current is spectrum and matrix elements. That I invent, inspired from the random matrix theory, and that's all I use from the random matrix theory.
You compared the two graphs, one with the system and one with the random matrix theory.
No, there is no system. I'm just doing toy models one by one some points. This is the system. That's all I know about system. You could ask whether there's some microscopic Hamiltonian which gives you this. That's a different story. Yeah. So maybe third part of the talk will be that of one particular model. So let me just quickly go through other options. So other toy models. So inspired by the power law divergence of a 2-point function in conformal quantum mechanics, we wrote down one more model. So this again doesn't look like too much of conformal quantum mechanics model, but what you could check is that this satisfies the KMS relation, which is a strong self-consistency relation model in the 2-point Weidmann functions. And if you set this parameter phi naught to phi by 2, it reduces to this familiar sinh phi p by beta, which is the finite temperature 2-point function. So in conformal field theory, so conformal quantum mechanics also. Anyway, so this is the model that I'm writing now. Maybe I should just say something that, these toy models are not out of the blue. In the third part of this talk, which is the SYK model, you will see all these toy models coming together. So that's why it is model.
All of these guys have a singularity at equals to 0?
No. This will not have a singularity because t equal to 0, it's fine.
Fine. But don't we expect a singularity? Oh.
No, this is just inspired. I'm now writing it down. In fact, I don't want something which is singular because if it is singular, I cannot track the transients. I mean, you need something with the cutoff. So this phi naught kind of acts like a cutoff.
Nice. So phi naught equals pi by 2 has the singular.
So at this level, you might think phi naught is just a regulator, or it's a parameter of this model. N is like the conformal dimensions. So these two models define these two parameters define the model phi naught and N. And you just to say that I'm not giving you a dense spectrum yet. I'm not giving you a matrix elements average yet. I'm just giving you the 2-point function. We will later on see an example where we can construct this 2-point function from some known models.
Just sorry, you must go on.
Yeah.
Isn't beta cutting it off in general?
No, I find a very small value of the beta there and the beta there cancels. So it's of course pi by 2 minus t of sine.
Okay.
Yeah, small t divergence doesn't care about temperature. Yeah, again, what we wanted to say, or what I want to say is that if you compute the heat current using this model, kind of all the things that you expected works out. There is a peak.
What is the temperature difference you have there at the steady state?
Here, yeah, I think I didn't write it, but yeah, so order one.
You have two particles, two baths, right?
2 baths, yes.
And then you are connecting. But the baths are kept at those temperatures?
No. Yeah, so you just take 2 systems and then connect them. That's all. Initially, it was at that temperature, and then there is no temperature.
So that is only for a short time.
Yeah.
You don't commenting on this. You don't wait long enough to see the temperature.
No, but it is carbs saturate. That's why
saturate. So saturate.
That's a steady heat current.
If you went long enough, the temperature difference would change, so that current would go down. But you're not waiting like that.
So this is not the system energy. This is the system currents. This is not equilibration.
No, that's fine. But for equilibration to remain non-equilibrium or whatever to remain steady, I need to keep these two things at these two temperatures.
Yeah,
right?
But that will only be visible in the next order perturbation.
I think the time for that will be like 1 over epsilon, 1 over epsilon square.
So 1 over epsilon square. Yeah. Epsilon is the coupling to the mother. Yeah.
And my perturbation, I'm doing perturbation theory.
So he's just looking at time square of it.
This is order epsilon or?
Yeah. No, not order epsilon, order 1.
Order 1.
But epsilon is small, so 1 by epsilon is not visible. I cannot trust this.
It's a perturbation theory
in epsilon. Yeah, maybe some combination of epsilon and time, but for me now, epsilon is small and time is order 1. That's all. Yeah, so now again, the same questions that we could ask. You can see transients, we have characterized the transients, I'll not show you.
But then this long-term behavior, should you be looking at them with this? Because your actual long-term behavior will change from this.
Yes.
Right? Because the answers from those singularities are only about very long times.
Right.
Right?
Yeah. So, what I'm saying is that here is a regime where there is a steady heat current.
No, I'm asking within your calculation, should you go to that regime where the power law is visible? At that point,
Yeah.
your next order.
No, but epsilon can be as small as I want.
You can make it epsilon as small as you want.
So this power loss will
No. The point where the power loss take over also go further and further.
No, that's the point. That here there is, the power law is hitting it within order 1 times.
What is power law? Power law means
Approach to power law.
Yeah, power law.
Sorry.
Sorry, here it is exponential because this is a different model. But here it's much faster. Yeah, but in the RMT story, what we saw was that power laws were order 1.
You get to power law by order 1 for small epsilon coupling.
Yeah, I mean, it's maybe numerically, what I did was we can do perturbation, large T perturbation theory, and then kind of reverse.
The last thing to order epsilon perturbation theory should not be done. That is the first problem.
No, you could say epsilon is the smallest, and then T is sufficiently large, but not as large as 1 by epsilon.
So there's a reason I'm saying this. When you have a singularity anywhere, right, you get this, but you also have a smooth rest of your whatever density of states and coupling, and which will give you an exponential decay.
That would have died out.
That dies out over a scale, which is TB over epsilon square, bandwidth over epsilon square. So when you make epsilon very small, these are all calculated in more realistic models. Right? So these things die out because you make the coupling weak, your exponential die out is also weaker. Right?
I'm not very sure.
Estimate what is the time scale over which your other smooth part will die out. That is TB over epsilon.
Maybe I just understand. So the epsilon is as of now just an overall number. Epsilon square times heat current will be epsilon square times some integral over 2-point function.
Epsilon square is a coupling to the one, right?
Yes, right.
So roughly speaking, the bandwidth divided by the coupling square, right, is a time scale. You can convert it to energy scale, and then everything will give you a time scale. This is the time scale over which your smooth part, which gives you your exponential decay, will decay, and your power laws usually take over after this time scale.
Yeah, so this is where I don't think I agree, because somehow maybe there's a way to formalize it.
Analytically from the Fourier transform. This is not even perturbation.
We only care about 2-point functions because it's an integral over 2-point function. 2-point function doesn't see epsilon. It's a system 2-point function.
Yeah.
It doesn't see epsilon. Epsilon is a particular coupling of the 2 parameters.
Yeah.
And it doesn't see, the system doesn't see the epsilon. Maybe in the initial picture that I had, there is hot and there is cold, and I'm coupling them by an order epsilon. And then heat current will be an integral over some 2-point function.
Correct.
That's it.
Correct.
I don't remember exactly, like something like this. Now, what I'm saying is that this has some characteristic fall off. In the random matrix theory case, it has some fall off, and from this I can estimate how it approaches the. So this has a behavior which goes like this. Let's say becomes a constant, and I'm trying to extract the powers here, and that has nothing to do with epsilon square. It's just it's just coming from here. I'm maybe saying it in a very technical way, not in. Yeah, I don't know. Maybe there's a more intuitive way of saying this.
So you are using the Baer-Green's function.
Baer-Green's function. Right.
So your Green's functions are
not getting
due to your coupling.
No. Yeah.
But is that a correction?
Well, this is what I did. I agree.
And that is why your things are going to a steady, because if you have kept it at H and your Green's functions have not changed.
Yes,
they are at H and T.
Right.
Like somehow you're pumping energy and maintaining them.
Right. That's what I did.
I see.
Yeah. So we see
then whatever is conducting is nothing.
Whatever is conducting.
See, normally the conductivity is the property of the system that is conducting.
No, there is no system. There is this 2 operator connected. There is no channel here. It is just OH-OC channel. That's our Hamiltonian is the interaction.
I see. So then we should not expect naturally Fourier's law will not come, because there is, as Srini was saying, there is no length, there is no concept of actually a medium getting.
But here there is a Fourier's law like regime. That's what. the point.
उसमें L लगता है because वो Q आता है. Q will not be defined, no.
But in Fourier law, he only means
What I mean is,
you want to
yeah, maybe the
that
heat current is proportional to temperature.
Okay.
It will still be pronounced for temperature.
Maybe in the interest of time, maybe we can
Here's the short.
Yeah, right, right.
then have the
Here's the short
questions for you.
and he's eating them.
So, yeah, so what I wanted to say was that there is an exponential approach to NESS, and we can actually calculate thermal conductivity. It's something in terms of phi naught and m.
So this is what I explained.
Here's my question: is the thermal conductivity of what?
Thermal conductivity of, yeah, I'm not going to say there's a channel, but it is just this. Yeah, so
No, but when you say thermal conductivity,
heat current divided by temperature difference. That's what I'm
that's
saying.
not what I'm saying.
Hmm.
I'm typically talking about thermal conductivity of a system.
Right.
You have no system.
No, I have
You
no
have just 2 baths you have connected through a short.
Right, right.
This is the conductivity of what? That is the question.
Let's not call it that.
Yeah, maybe.
Let's continue and then let's continue and maybe have the questions later because you are already halfway there, right?
Yeah.
Now I like this expression for your NESS. It makes sense to me.
Yeah, this is what usually would be quasi-particle kind
I
of
don't
a.
understand the power of, except when Rajdeep explained that it's due to a kink in your
Yeah.
system.
Yeah, I can maybe catch it later and explain more, see whether I can. So just one small version of this model, which is also doable, is that if you take m large, now operator dimension to be large, holding this other parameter phi naught, scaling the other parameter phi naught in such a way that this parameter is fixed, this 2-point function, which was this cos phi naught, you see, becomes a Gaussian. So this was one of the things that, so you could ask whether this 2-point function is, let me just say that there are some there's a choice of spectrum and matrix element square, which gives you this 2-point function. This spectrum is exactly what people had anticipated before, just a Gaussian. And there is some choice of 2-point function, which gives you exactly this, choice of matrix elements, which gives you exactly this 2-point function. I will not bore you with the details. So again, you can do transients, and turns out that the approach to NESS is Gaussian. Conductivity can be calculated. Let's not call it conductivity, but yeah, can be calculated, and it shows some Gaussian behavior and inverse temperature. Again, just to kind of quickly summarize what we did. So till now, I only looked at toy models, RMT-like toy models and conformal-like toy models. These are not genuine quantum mechanical systems. So there's no Hilbert space, there's no operators. You couldn't, yeah. So for example, the perturbation theory, next order, we could not do in principle because we don't have concept of endpoint functions. So are there genuine quantum mechanics models where you can do this? And now I'm going to talk about next is this SYK models and one particular limit of it. And this is the reason why I also discussed the various toy models before, because they're inspired by this SYK model. So let me just quickly flash through you. I guess most of you know about SYK models. I don't need to discuss it. So large N is done by Schwinger Dyson equation. What I want to kind of leave you with is that it's solvable at low energies. That's what the Schwinger Dyson equation has, property that it's solvable at low energies. But people typically do numerics at higher energies, and that is what I'll come back to later. There is a version of the SYK model in which there are p fermions interacting instead of 4 fermions. That's what I will be dealing with. And just some of the features again very quickly. 2-point functions can be computed. Lyapunov exponent is maximal. Low energy field theory is some Schwarzian, which is dual to some gravity. So it's interesting for various reasons. But for our purposes, what I want to say is that this G of T, or this density of the spectrum and matrix elements averages, are known, at least at low energies analytically and higher energies numerically. So this question has been addressed. So what happens if you take 2 SYK systems and put them in contact, just like this thing that I did? And there is existing literature on it. I will not say much about it. The only thing I'll say is that whatever they get, we also kind of get. So I won't say much about it.
Will you tell us what the chi of beta is?
Chi is the 2-point function.
Okay. Of what? Of fermions or bilinear?
No. Sorry. This chi is just this fermion chi. And you are asking what operators I do?
Correct.
Yeah, these are kites. That's what they did.
With fermion.
Single fermion from here, single fermion from here. That's what these people did.
Single fermion from here with single fermion from there.
Yeah.
So making the ON invariance of this and ON invariance of that.
Yeah, but ON kind of
was a
statistical anyway. So
these are Majorana, or
these are Majorana. These are not complex SYK.
So I will change the parity as I talk around. Normally,
there's no. There's just two.
When you are coupling a chi from here to here, Majorana is going from here to there. So, but normally those are done in terms of the actual complex fermion, right? Because you have some fermion parity, etc.
You want to preserve it. Yeah, it kind of doesn't matter so much. That might be what I would say. What we will do is not for that fermions. We can have a slightly more complex bilinears or anything. So maybe we'll just talk about that. This is what they did, is what I remember.
I don't know what you do, but just, I mean, if you start with a state which is sufficiently entangled between the two, then this is tied to this Gauss-Jefferies kind of, being able to efficiently do teleportation, right? I don't know whether that's something interesting. Whereas in the same system, right? So.
No, he's completely unentangled.
He's completely
and then he's coupling them through something, right?
Yeah.
So where he is going
if you had entangled, it would be that more interesting.
That would be the more
gravity side actually.
So this is more similar to Maldacena. Yeah, this is somewhat similar to Maldacena key models.
Maldacena key model of an array.
No, he has this kind of system.
2 years.
Quantum dots connected.
Okay.
Yes. So,
sorry.
Right. Anyway, what I wanted to say was that this is done numerically at short times, but analytically at long times. Now, is there some model which you can control at shorter times? And the answer is that there is a version of SYK, this is called the double-scaled SYK. I'll just quickly go through it, which is that P also becomes large as square root n, such that P square by n is fixed. And this lambda acts like a 2 parameter, and you can calculate various things exactly in lambda. The operators which we use to couple the two things, as Shiraz and Prithvi were asking, were again something which is very similar to Hamiltonian, which is built out of string of fermions, but with its own disorder. And the only thing I want to say is that it's the number of fermions is m times bigger than the number of fermions in H. Roughly speaking, you see that this in the conformal regime, Hamiltonian itself will become dimension 1. And then this will be m times heavier than that. So this roughly plays the role of operator density.
This is like coupling the two systems at their boundaries in the gravity description. Because this is like a single trace operator. You're turning on a trace times trace.
Yeah.
So that's connecting the boundary conditions of the two systems.
Yeah.
So the Hawking radiation will lead to the temperature equilibrium.
Yeah. So
beginning to light entanglement.
No, just two different systems, two different boundaries, and then you link their boundaries.
I should say this, that Loga tried to do this with some of his students in ICTS, but it didn't work out. Yeah, right.
In fact, I know exactly what I'm saying.
Yeah, he tried to see whether Hawking radiation will do that.
Yeah.
But yeah, anyway, I don't want to say anything because I don't know that calculation.
With the entanglement, the wormhole will up. Without it, we just have to disconnect.
Yeah.
So this is
Sorry?
This is where your basically a self energy and you just have 2-point hyperlocal 2-point coordinate or in some large element. That's the double scaling limit.
Hyperlocal 2-point. I didn't get the question.
Like, only 2-point functions are relevant. You can ignore all the
No, that is not true. Connected. I mean, the higher point functions can also be computed, and it's very non-trivial.
Yes.
It doesn't become classical in that sense. There is a limit in which it becomes classical, but in small lambda limit something.
So physically, where does this parameter in what expansion?
Yeah. You mean what's the diagrammatic expansion kind of thing? So that I'll say something about it, but it will not be very good. We'll just come back to it. So again, to tell what kind of things are known, endpoint functions are known, at least written as an integral over some special functions. SYK physics is completely there. You can recover it in some special limits. when lambda goes to 0, lambda is roughly like p square by n. So if p goes to 0, you recover SYK. Lyapunov exponents can also be computed. Now it has a lambda dependence. In the SYK limit, it is 2 pi by beta, which is maximal, but now you can compute it at least order by order in lambda. People have done that. There is a proposed dual for it, which is dilaton gravity, but with the not linear potential, but sign potential, sign Q dilaton gravity.
Later, is that duality established? Is it conjectured? What is this?
I think there is more evidence building up. There is another kind of duality, which is the DSSYK, that I don't understand. The double digital SYK, that I will not comment on because I don't understand it much. But this one, at least it's concrete, and I think there is more evidence these days about it. I can take you.
Is there something discrete about the bulk in that?
No, that's a surprising thing. There is, just dilaton gravity with the weirder potential. That's all.
Yeah.
So the dilaton is periodic, right? And that leads to quantization.
Right.
Oh.
Yeah. And also, as one of my colleagues used to say, there is non-commutative gravity can also be kind of recouched in continuous versions. So at least in 2D it can be done. So anyway, so just to say one small comment about diagrammatics, this is not Feynman diagrammatics, but it's more of a combinatorics. I will maybe skip this slide, how this is solved, double scale SYK is solved. But what I will leave you with this, the density of states is known. It's a dirty looking function, but it's a special function. It's written in terms of no, there is a nice mathematics behind it apparently, because everything is Q deformation of something. No, that's the thing. There is.
That's looking for.
sorry.
But by the way, I missed this.
By the way, the dirty superconductors are whatever. If you say dirty, it's not very bad thing. That's not physics.
Then what is theta mean?
Theta is just a parameter. That's all. I mean, it runs from 0 to pi. E is again a cut, just like random matrix theory. There's a cut.
Sorry, I understood what Q was. It's this ratio of E.
Right.
What was theta in the underlying model? Sorry.
Theta is not there. It's just energy. Energy is written in terms of
energy.
Yeah. So there are special limits where again things look very similar. So Q equal to 0 just happens to land on the Wigner semicircle. Q equals to 1 happens to land on the Gaussian model that I discussed some time back.
So Q was what?
Q is the lamp. Yeah, maybe I should write it down because I'll keep using it. So P square by N is lambda, and e power minus lambda is Q.
So Q equals 0 was like what are you doing?
Q equal to 0 is the random matrix. So Q equals
0. So P square.
Q equals to 0.
Is like
lambda going to infinity.
Oh, lambda goes to lambda.
Q equal to 0 is lambda going to infinity. And SYK is on the other side. Q equals to 1 is lambda going to 0. So SYK sits on the lambda equals to Q goes to 1. That's right. So this is how the density of spectrum looks like. Maybe, can I take 5 more minutes? Okay. Sorry for this. So this is how the spectrum looks like. There is a finite cut, but the cut goes off to infinity if you take Q goes to 1.
So at any finite Q, you will be, your density of states will be smooth, or you will lose the Wigner, the cut, or the unknown density of the Wigner.
Yeah, it will be smooth everywhere except at the cut. I mean, there is always a singularity. That's maybe I'll say in the next slide. I'll show what happens at intermediate Q. You could ask, and what happens is that the edges always behaves like an RNT. It's like a renormalized RNT because there is some coefficient, but edge always behaves like an RNT. There's a square root singularity. But then,
is there in the non-double scale standard SYK? Of course, you do get the cut when you include the one loop, but then you have this exponential number.
Yeah, that is not there here.
And that's a very characteristic, beautiful. You don't have that.
It's there, but it gets cuts off somehow.
You don't have, once you go just a little beyond the cut.
Yeah, you will see that. You will see that. Yeah, you will see that in the next
slide. Interestingly show up in your.
Yeah, it's there. It's there. Because all the SYK is there here. You just need to go into that limit. To see the SYK limit, you need to go lambda goes to 0, and then you see this kind of long region emerging, which is exactly like what you're saying, exponential growth, very large growth.
Nice.
So you can kind of see it here. Well, you don't see it here, but sorry about this line. So what I wanted to show here was that there is a large parameter because lambda goes to 0. So there is all the, there is saddle point techniques available at this region, and that's why this becomes solvable again at lambda goes to 0. So you can do a little bit of more analytics. So I'll just tell you what's the bottom line. In what limits it goes back to the old model I already described in very detail. So as I was telling you, at the edges, at very low temperature, you see only the edges. So you go back to the RMT, and the quantitative thing is that if temperature is sufficiently small compared to Q in some scale, you get back the RMT, slightly renormalized RMT because you have to you have to kind of, so delta, and you have to read off what delta and F naught is.
You get back the edge of the RMT.
Edge of the RMT.
But the RMT was dominated by its edge.
Yes, that's what I told you about power law, conductivity, all of them are just basically decided by the edge. And then there is this other limit. Q goes to 1, of course, is Gaussian. And there's this SYK-ish limit where you take lambda goes to 0, but then you fix phi naught in terms of temperature and Q in some way. Okay, this is how you set it. You get the conformal models. Okay, so the toy models that I told you, I don't need to say anything more about it because you already know everything. In those limits, you already get phi naught, was the parameter in the conformal model. Phi naught equals to pi by 2 reduces to the usual sine pi by 2.
So you have to set the conformal model to some value of phi.
Yeah, and depending on the temperature and Q on lambda. So this is the thing. When Q goes to 1, this picture simplifies. So let me just show you the, or lambda goes to 0, there's a cleaner version of this formula. We at very low temperatures, and there's a scale in the problem, 1 by lambda to the power 3 half. At very low temperature, you see RMT-like behavior. If you crank up the temperature, you see it's conformal-like behavior. And I'm just flashing the formula for the conformal regime conductivity. Just we had it before, but just to this context again. So here in this regime, you have this conductivity, power law kind of conductivity. Finite Q, you can do numerics because these functions are not very nice. So you have to do numerics. You have to resort to numerics.
You said this, I should slowly now, but if you are in the conformal window, how does the approach to NESS look like? Not power.
Exponential.
Exponential.
Quasi-particle like behavior. Because this is the SYK region. And you expect some kind of quasi-particles floating around.
Yeah, no quasi-particle. You must think conformal.
Sorry, maybe I'm saying it wrongly. Quasi-normal modish.
Quasi-normal modish. Okay, yes.
So, so thermal conductivity, as the feature that I told you, the loose graph that I showed you at lambda goes to 0 survives, even at finite Q. At finite Q, you kind of see that this is numerically plotted. You can see RMT-like behavior, you can see conformal-like behavior. In intermediate regime, you cannot, I cannot analytically show it, but I can numerically see that it's something smoothly goes over between this and that. Interpolates, that's true. Transients can also be computed, as Rajdeep was saying very in the beginning. There's a linear team behavior in heat current. You can, in fact, do perturbation theory. You can compute T square, T cube, all of these things fairly easily. Those special functions admit nice perturbative expansions. Anyway, let me just summarize. I think summary is okay. I just looked at the heat flow between two quantum mechanics models. I looked at heat current, characterized various features of it, looked at various toy models, and show how all these toy models come together in one concrete realistic model, which has chaos, this double scale SYK model. So let me just do one or two quick future things. So as people have already said, it would be interesting to see thermalization. Of course, it's non-perturbative in epsilon, but it's DSSYK, so there is some control. All the endpoint functions are kind of known as an integral, but known. So you might be able to extract more. Another thing is that, what happens if you look at chains, not just 0 plus 1D system, you keep SYK dots, and ask what's the transport. These kind of studies are well known in SYK literature, but nobody has done the DSSYK version of it.
So nobody has done DSSYK chains.
No. So, and it might show some kind of, you might see the heat diffusion-ish kind of behavior. DSSYK is related to deformed electron gravity, as I was telling you before. And what is the gravity picture, one could ask. These are all slightly big picture questions. What I am doing these days, again with Loganagam and another student in ICTS, is charge transport. There are versions of SYK model in which there is U1 charge. And you could see, and there is some subtlety with the DSSYK limit, the double scale limit of it, but we are hoping that we will be able to solve it. And if so, then we can do charge transport. This is much more interesting for various other reasons. For example, simple things like Widerman-Franz law, which is, thermal conductivity and charge conductivity are related. It's true for quasi-particle theories, but these are theories with no quasi-particles. Are they still true or not? These kind of questions one could in principle ask, but yeah.
That you can just compute even for SYK, charged SYK.
Charged SYK, yes. Yeah.
Because at low temperatures,
right.
In the
People have computed it. People have computed it. So that itself is not very new, that I agree. But yeah, you have a more conditional version, that's all I can say. Yeah. This was numerically seen, that they were proportional to each other in SYK also.
Because you have the Schwarzschild and the rotor, and that should cover all of linear transport. See for the plan. Okay, we should talk. I'm 100% sure we can do it.
Yeah, okay. There are some limits where I've seen analytical.
One question, when I think of transport of a system, I'm transporting something from one end of the system to the other. Where you have two SYKs or two DSSYKs and you are putting a short and then you are asking how much it is going between them. Presumably you are pumping them so they are at the same temperature.
Not yet, but
so on. Why do we expect anything close to Widerman? Because this is conductance, if at all, not conductivity.
Yeah, so
France, the Q going to 0 is very important to have those kind of.
Yeah, so I think this is maybe when there is a channel kind of. There is a channel.
And then there is a property of the channel. Conductivities will be what is carrying your heat in the channel, right?
Right.
That's not your SYK. Your SYK is the bar.
SYK is the bar, that's true.
So why do you expect anything?
I would say, even if you have a channel, it's kind of equivalent to some kind of operator coupling, because
operator coupling will not give you conductivity. That is what I'm trying to say.
Yeah, so that's what I think that's what maybe we can discuss this later, because I have seen calculations in SYK where there is a channel, kind of channel, but still it gives you roughly the same result as this.
It can give. I'm just saying, see, conductivity is property of water. Decide what is carrying the heat.
Yeah, here also there is some operator which couples the two. There is some operator details. The conductivity will depend on the operator detail.
You can only define conductance.
Maybe
conductivity requires you to divide by, because transport is about how fast I am.
Sorry. I think I am using the wrong word here. So maybe
conductance.
Yeah, conductance.
For conductance, there is no Widerman transform. Even in I give you a piece of metal, its conductance between all sorts of shapes and so on. What is Widerman transform?
Okay, so maybe I should say that in the SYK model it has been done, and people have done. Well, the comment that I mentioned was that Widerman-Franz law you might be able to see it. SYK people have done it and commented on it, that there is a Widerman-Franz law here.
How do they calculate conductivity?
Yeah, maybe this is what they call conductivity.
And all linear response coefficients can be worked out. Let's put it like this. I don't know.
So this is what they call conductivity.
I can see the origin of your version of Widerman-Franz law is that the same objects carry heat and charge.
Yeah.
You don't have different particles contributing more to heat and some others contributing more to charge, because you will ultimately have a real fermion. An actual complex fermion from one drop to another drop. Nothing else hops.
Right. So the same guy which carries charge and the energy is what you lose.
So therefore there is a fixed ratio because there is no other entity.
Anyway, so the last question I wanted to leave it with is that, here is a model which is solvable, chaotic, no quasi-particles. What are the interesting questions that one could ask? So I'll just leave it there.
Okay, we had quite a bit of discussion during the talk, so one or two other questions.
Aside from the bulk, you could couple two equal four angles at the boundaries. And compute because of Hawking radiation heat flow. Is that of interest for somebody? Take two equal four angles there is. Now, couple them at the boundary, you have, let's say, Lagrangian with Lagrangian. That coupling. That turns source of one.
What I know is that source of one is the expectation of the other side.
So now Hawking radiation mode comes, it changes the wave here, therefore it produces a source there, so it sends some energy in. This should be a doable calculation. Is this of any interest?
This is what I thought Loga was doing, and he said that he doesn't get any. So doesn't get any.
He's working with some weird two-dimensional model or equals for you.
But he was not doing 2 dimensions. He was doing generic gravity systems.
Okay.
So yeah, I don't know whether he's going to talk in ISM.
I don't know.
I know he's going to talk in ISM. It might be partly this and partly something else.
Can I ask one question about which I wanted you guys to pay attention to their private Let me just ask this question, which I don't know well enough, which is, you didn't talk about entanglement, but just to ask you, I mean, what is the relation between how systems thermalize and how entanglement spreads is not very clear to me in general, because entanglement spreading is often ballistic with the butterfly velocity, and thermalization is often diffusive, right? And in the few cases I've seen, the relation is kind of complicated but interesting, and I don't know whether there's you might think there's some universality to this, or there's no universality to it, or what? I mean, that's just one question which seems to be getting interesting. People have studied how entanglement.
I think it's a very interesting question, and I have seen some literature. But I don't know if there is any understanding of universalities.
No, I don't know the relative.
But yes, they often tend to travel with velocities, and even one is diffusive and another.
But the point is the following, that entanglement involves all correlations, in principle, all endpoints that you will have in your whatever subsystem and so on. So, and when people talk about thermalization, they are often looking at what the 2-point function is doing. So you should ask whether that is a good definition of thermalization as well. I can have a 2-point function which is decaying exponentially, right? I can have a 4-point function which just flows with a velocity. Once I have that, my entanglement spread is taken care of by the velocity, and you will not care that I will have a diffusing 2-point thing, right? So to say that these, you will technically you will have to show every endpoint function actually decays exponentially to make the statement that thermalization is exponential or diffusing, or it goes diffusively, spreads diffusively to make that statement.
But it's the other way around, right? The entanglement spreads faster than any of these.
Yeah, because often 4-point functions spread far. I'll give you one example, right? 2-point functions can be massive.
Right.
But I can write down corresponding 4-point functions which are gapless. Green's functions per convolution that can become gapless. No issues with that, right? And this happens in condensed matter all the time. Take a superconductor. Single particle is gapped, 2 particle is gapless, right? Because you have a Goldstone mode or something like that. That's it. Right? So then, suppose I have such a situation, which when I'm saying what is thermalizing, I'm just talking about one particle correlation.
Maybe we can talk about, we can make it a little more precise by saying, take some conserved quantity like energy or something, which spreads diffusive. Okay, then you have diffusion constant and you have butterfly velocity. Now, in many cases, okay, like if you take SYK chains, the diffusion constant goes like the square of the butterfly velocity. It would be interesting to ask if something like this is generic. Why is it generic? I don't know.
But you are asking the first question. Is the entanglement being carried by the 4-point correlations or 2-point correlations? There is no particular reason it should only be carried by the 2-point.
Well, okay, we'll talk more, but let's define a butterfly velocity through a 4-point overall. Okay. So all I'm saying is, at least in SYK chains and so on, there is an interesting relation. Now you can define butterfly velocity in other ways, but okay, let's take the overall. I mean, is there some generic relation between entanglements where that, energy diffusion, let's say, or that might be a more precise version from that. I mean, it would be interesting if it's, okay, anyway, sorry, I just thought I was.
Okay, let's thank Prithvi again.